so we're going to find them all. We'll find all the rational zeros. What we'll do is I'll show you first how to use the new little piece of revelation that we're going to be given. And then also we'll do one example where we're actually finding the zeros of a polynomial. And then the rest of it will be you working. It's a short day. Tomorrow we will just continue this. The goal for tomorrow is we're just going to review what we did last night or didn't do last night. It should be like tonight. And then we will do 3 problems. Yes, during class. During which point in time I'll help you. How's your breakfast going? Those money buddies?
Looking at me.
Those are good money buddies. Is that a panini? Oh, I can't see. So here's the really, really cool theorem that helps us do this much more quickly. It is called the rational zero theorem.
What have we been using?
We have been using Descartes' law of signs, where we count the sign changes and we figure out how many positive and negatives there are. This is called the rational zero theorem, which means if a zero exists, there is a way to find all the possible zeros that are rational for a polynomial. And the best way to do this is not to look at the words, because that's just confusing like letter overload. But if you look at the example, if this is a cubic function that we have, and let's say that 3/2 is a 0, that means that 3 is a factor of the last term, and 2 is a factor of the first term. So it's really best to look at this conversely. If you want to know what the possible zeros are, you look at the factors of p and q. Where did I point p? P is over here. Where's q? At the end. So p, did I do this backwards? So hold on. I am recording this. I'm sorry I messed up. Please forgive me. Okay. Q comes first, P comes last. You would think that alphabetically, but it's not. So you come up with all the factors of P, you come up with all the factors of Q, and you divide. P divided by Q. So in this particular example, Q is 2 and P is 12. So what are the factors of 12? I didn't ask you what are the prime factors. But what are the factors of 12? Well, I could divide 12 by 1, and I would get 12. What else can I divide 12 by? 2, and I would get 6, and 3, and that would give me 4. Is that it? How did I know I was done? I started with 1 and 12, right? And then we went to 2 and 6. If I approach the middle, and the middle numbers are close together, it means I've got them all. How about 2? What are the factors of 2? 1 and 2. So once you get the factors down of P and Q, this is annoying that this is Q and this is P. All the possible rational zeros of this function are P divided by Q. Those are all the possible rational zeros. So what is one possible combination of P over Q? You could have 1 over 1. So I could do like 1 over 1. So one possible zero would be 1. Now that's positive and negative 1, so all of these are positive and negative. What's another combination of P and Q? You could do the 1 again at the top, but then use the 2 on the bottom. What would that give me? 1/2. I find it best and easiest to list all the whole numbers first and then the fractions at the end, because I like to start with the whole numbers, because whole numbers are easier than fractions. And then if the whole numbers don't work out, then I go to the fractions. So if we keep the denominator 1 for now. All my possible rational zeros are 1, 2, 3, 4, 6, and 12. Positive and negative. 1, 2, 3, 4, 6, and 12. And then I have all the fractions that come with it, which just make all of these half, right? So 1/2 is 1. Then there's also 2 over 2, but I already know that 2 over 2 is 1. So I'm not going to write it twice. But I can do 3/2, and what else? That's it. Because all the other combinations with a denominator 2 yield a whole number, which I've already written down. Right? 4/2 is 2, 6/2 is 3, 12/2 is 6, which I already got down. And this is still plus or minus even on the fractions. Why is this good? This is good because you won't be stabbing in the dark and spending all night trying to find zeros. Now you actually know where to look. So you can use Descartes' law of signs to figure out whether these should be positive or negative, right? And then you can use this rational zero theorem to figure out which ones to plug into your synthetic division. Last night for your synthetic division table, we just had a list where we started with 1, 2, 3, 4, and then we kept going until we got one that worked. Now, I'm not telling you to start with 1, 2, 3, 4, 5. Pick the ones that are in the rational zero theorem, that the rational zero theorem yields for you. Because that's where the rational zeros will be, if there are any rational zeros. Then, this P over Q business. That if it's a polynomial with rational zeros, then those rational zeros will exist at these values. Some of these values will yield a remainder of 0 when you do synthetic division and you set up your table. Okay? So when you do your table like we did on our assignment, this one here, when we make our table, instead of just starting with 1, 2, 3, 1/2, I'm going to start with these values. 1, 2, 3, 4, 6, 12, 1/2, and 3/2. Okay? Because I know that if it exists, it's going to exist there. So I'm not going to try 5, because that's not going to work anyway. That's what the rational zero theorem tells me. This will make sense as we do a couple of examples. So for example 1 here, we're not asked to solve this, we just have to list all the possible rational zeros of the function. So looking at the function, and I got this wrong last time, P is at the end and Q is at the beginning. Right, Casey?
Yes.
There's P, there's Q. P is always your constant term, and Q is always your leading coefficient. So I find it helpful to write I write the factors of 9 and 2, and then I write the combinations. It just helps me more, because I get confused. You know, I'm not Mr. Hill, I haven't been doing this for like 30-something years. No offense. So for 2, what are the factors of 2? 1 and 2. What are the factors of 9? 1 and 9 and 3. So now I can write all the combinations of P over Q. P over Q, and this was Q, and this was P. So what are the possible zeros? Well, pick a P, pick a Q. Let's divide everything by 1 first, because I like whole numbers. So that would be plus or minus 1, or 3, or 9. So plus or minus 1, plus or minus 3, plus or minus 9. And then how about when the denominator is 2? 1/2, 3/2, 9/2. So should I just randomly start plugging these numbers into my synthetic division? Or is there something else I could do to narrow the list down a little bit? Yeah, do Descartes' law of signs. Let's narrow the list down before you get started, because the last thing you want to do is try all of these. 1, 2, 3. I don't know. I mean, I have to try this law of signs thing and see how many possible positives are there How many possible negatives are there first? So what are the sign changes in the positive respect? How many are there? 2. That's bad news, right? Because it means that there are 2 or there are none. How about the negative sign changes? How many negative sign changes are there? This one becomes negative because it's odd. This one becomes negative because it's odd. So how many are there? 1. So when I do my synthetic division, which values, which numbers am I going to start with? I'm going to start with the negatives. Why? Because I know there's 1. Right? I could do the positives, and there could either be 2, and I could find them right away, or there could be none, and I could just try all 6 of these with no luck. So you have to do a little bit of thinking beforehand before you just start randomly guessing. So if you start with the negatives, that's going to help you, because you know that 1 exists. Question, Waverly? The odd, when I try f of negative x, all of the odd degree ones change signs, right? So that's going to yield this one is a negative 2x cubed. That's a negative, so there's no sign change there. It's a negative 11x squared. There's no sign change there to negative 12x, but there is a sign change here to positive 9. Why don't I change this positive 9? Because if I multiply by a negative x to the 0 is still 1, and 1 times 9 is still 9. Because there is an x here, you're right. But it's x to the 0 power, right? Which is 1. And even if I make that a negative x to the 0 power, it's still 1. So 1 times 9 is still 9. So I knew there was 1 negative sign change, which is why I would start in my synthetic division table with negative 1, and then try negative 3, and then try negative 9, and then if that doesn't work, then I go to the fractions and try those. And then if none of those work, I know I messed up, so I would do it again. So we're not actually finding them in this example, we're just listing all the possibles. Ready to try one now? Yeah. Stoked. We get 10 minutes, enough time to do one. Okay, we're going to find all of the zeros of this quartic wheel. So you have the choice to either start with Descartes' law of signs, or you can start with the rational zero theorem. I like to do the rational zero theorem and then use Descartes' law of signs, just so I can cross out all the little pluses and minuses. It makes me happy. But you can do however you want. So I look for the positive sign changes, or you can just come up with the factors. I'll just do the factors. P over Q. My P is the last one, my Q is the first one. Thank you, Casey. Ooh. Why did I ooh? Well, because there's a 60. Okay, factors of 60 and the factors of 2. At least the Q is a 2. That's nice. So we're not dividing by like thirds or sevenths or something. You know what might happen on a test. Okay, the factors of 60 are 1 and then 60. Notice I wrote the 60 all the way on the right because I'm going to fill in the gaps between these so I make sure I get all the factors, because that's my goal in life. Now 2 is also a factor of 60. And the other factor is 30. And then 3, which is 24, which is, cut it in half twice. Okay, thank you. Right, when you divide by 4, that's the same as dividing by 2 and dividing by 2 again. Because you multiply by a half is dividing by 4 because you multiply by a quarter. So if you ever want to divide by 4, just cut it in half twice. 4 and 15, 5 and 12, 6 and 10. Have I found them all? Yeah, 7, 8, 9 now. Yay! This is going to produce a list. You haven't seen a big list. It's when this number is like, 240, And this one's like 120, and you're like going on forever. So, okay. There you go, P divided by Q, and then we can make a list from that. I might just wait now and use my law of sines. This is going to be long, but we'll divide by 1 first. So the plus or minus is implied. Is that okay? I'm not going to write it.
Oh, yeah.
I'll put it in the front, and then you'll know that it applies to everything. So plus or minus, my options are 1, 2, 3, 4, 5, 6, 10, 12, 15, 20, 30, and 60. And then how about those fractions? Some of these fractions disappear because an even number divided by 2 can yield a number that's already in the list of whole numbers. So 1/2, 3 halves, 5 halves, 10 halves is 5, which is already on there, 12 halves is 6, which is already on there, 15 halves, 20 halves is 10, which is already on here, 30 halves is 15, and then 60 halves is 10. That's it. That's all there is. Now use the law of sines to let's narrow down the list even more. It's kind of fun. It's really rewarding when you get 0. Thank you. Once a nerd, always a nerd. Revenge of the Nerds. Here it is. Which one? I like 6. It's funny. It's like 80s humor.
Yeah,
That was a good decade. I was born then. Okay. How do the Descartes' law signs go here? 1, 2, 3. Okay, so your positives are 4, 2, or 0. How about your negatives? That one becomes, okay, stays positive, okay, positive. Oh, how many negatives are there? None. Yay! So now I go through here and I cross out the minus. Yay! Gone, 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 gone. Let's try the positive one. Till I find 1, and hopefully I can find 2, and hopefully there aren't 0. And then I'm just going to try them all if I can. Okay. What's that? It's not prime. I wouldn't give you something prime that would be like torture. You could like graph it and find where they are. No. Okay. Synthetic division. Here we go. So this is going to be 2, negative 13, 23, negative 52, and 60. One's a good number to start with. And what will be next on the list? 2, 3, 4, 5, 6. Now you may get to a point, one of the things I like to do is I actually like to do this table in my head. So once you do the table for a little while, try just doing it mentally because it does become a mental exercise. I find myself going like this a lot. But you don't have to do that, just do it in your brain, and it'll work out. Until you get a 0, and then you can write it on paper, make sure you got it right. But for the sake of time, I'm going to speed this up a little bit, which means I'm going to do this kind of fast. So if I make a mistake, here's a chance for an ace. Somebody already got one. I forgot who you were. You have to tell me. 2, negative 11. 12. That one didn't work. And if you already know it's not going to work, you don't even have to write the last number because you don't really care. So 2 is 2, and then 4 is negative 9. That's negative 18. I don't care. 3. 2. 2 times 3 is 6. Negative 7 times 3. Negative 2. Negative 5. I don't care. 2. So you just keep going, keep going, keep going, keep going. And then we'll find one that works, and we'll be so happy. 2. So 2 is 8. 5. Negative 10. Ooh, did I do that right? Negative 20. Ooh. You had a chance. You missed it. So that's negative 12 is negative 40. Negative 40 times 4, and I don't care. 2. 5, 10, negative 3. Anybody find it already?
I used Wolfram Alpha. I think there are 4 complex.
What? Shh. Don't cheat.
It's not cheating.
Oh, I found it.
You did?
I'm so happy.
What the
Yay! You almost have to do like a little dance when you get done. So there's my depressed polynomial. That's now cubic, and I need to find one more 0. Listen, this is very important. Don't forget, when you find a 0, what do you do with this 5? You try it again, because sometimes there are double roots, right? So now that you have the depressed polynomial, make another synthetic division table and do it one more time until it becomes quadratic, and use the formula.